Hey everyone, and welcome. Today, we are diving deep into one of the coolest frontiers in all of computing, that incredible bridge between the super flexible world of software and the lightning-fast realm of custom hardware. I want you to just think about this for a second. What if you could write an algorithm, in a language you already know, like C++, but instead of just running it on a regular processor, you could literally transform that code into a physical circuit, a chip that's perfectly optimized to do that one job at unbelievable speeds. Sounds a little like sci-fi, right? Well, that's the core idea we're going to unpack today. So to really get why this is such a game changer, we first have to talk about the heart of pretty much every computer out there, the CPU, or the central processing unit. And this right here is the perfect analogy. Think of your CPU as a Swiss Army knife. It's awesome, right? It's incredibly versatile. It can do a million different things pretty well. But if you have a really specific, really tough job, you don't want a generic tool. You want the perfect tool for that one job. And that's what specialized hardware is. It's a custom-built solution that gives you massive, totally optimized parallel processing power. And look, this isn't just some abstract theory. The source material spells it out crystal clear. Even a simple piece of code gets bogged down on a CPU. It just takes more clock cycles to get the job done. This is that fundamental performance gap that we're trying to close. Okay, so if we know custom hardware is so much faster, you might be asking, well, why isn't everything built that way? For a long time, the barrier to entry has just been incredibly high. It's kind of like trying to write a novel in a completely alien language. See, traditionally, if you wanted to design your own chip, you had to use something called a hardware description language, or HDL. And this is nothing like writing software. It's a deeply complex, really low-level process where you're describing the actual electronic circuits, the gates, the wires, the whole shebang. And this old way of doing things, man, it comes with a ton of headaches. You're working at a super low level, which means checking your work, verifying it, is painfully slow. Want to try out a different design? Good luck. That's a huge undertaking. And the whole thing requires a level of deep hardware expertise that most software developers just don't have. But what if there was a translator? Something that could take a high-level language that millions of developers already know and just automatically turn it into a detailed hardware design? Well, this is where our hero finally enters the story. Everybody meet high-level synthesis, or HLS. So what is it? HLS is basically an automated process that translates high-level C++ code directly into a hardware design. This design then gets loaded onto a really special, reconfigurable chip called an FPGA. You can think of an FPGA like a blank slate of circuits that you can program to perform one specific task perfectly. This right here, this is the bridge we've been looking for. And this just creates a radically simpler way of working. First, you just code and test your algorithm in the familiar, super fast environment of C++. Then, you use an HLS tool to automatically synthesize, or translate, that code into a hardware description. And finally, you deploy it as a high-performance circuit. It's that simple. The benefits here are absolutely huge for everyone involved. For the hardware experts, it means they can work at a higher, more productive level. For software developers, it means they can finally accelerate their most intense algorithms by targeting hardware directly. And because you can test everything at the C level first, the whole process is way faster, which lets you explore a ton of different design options to find the absolute perfect one. Now, you might be thinking HLS is just a simple, literal translator, but it's so much smarter than that. It's more like an expert interpreter who doesn't just translate words, but restructures whole sentences to best fit the new language. It's all about optimization. At its core, HLS understands that the end goal is parallelism, doing many things at once. It looks at your sequential software code, the code that runs step by step, line by line, and it fundamentally re-architects it to take full advantage of the parallel nature of hardware. One of its most powerful tricks is called pipelining. So look on the left. A standard loop is sequential, right? One operation has to finish completely before the next one can even begin. But a pipeline loop, on the right, that's like a factory assembly line. As soon as the first item moves to station 2, a new item enters station 1. The results? Well, just look at the data. You can start processing new data every single clock cycle, which in this case cuts the total time in half. It's a huge deal. And HLS can take that same idea and blow it up even bigger with something called data flow optimization. It essentially treats a whole chain of functions like a massive assembly line. As soon as the first function is done with its first piece of data and passes it along, it can immediately start working on the next piece of data. This creates a true, massively parallel pipeline, maximizing your hardware and your throughput. Okay, so this all sounds amazing in theory, right? But what does it actually look like in practice? Let's take a quick peek at the actual tools that make all this happen. It all kicks off in an environment that, honestly, is going to look pretty familiar to any developer out there, a standard graphical interface. This is the Vivado HLS tool. And you start things off just like you would with any software project. You create a new project. Next, you just add your source files, your normal .cpp or .c files. This is the actual algorithm, the brains of the operation that you want to turn into hardware. Nothing scary here. It's just the code you've already written. And this right here is a massive game changer. You also add your test bench files. This lets you run simulations at the software level to prove your logic is correct before you go through the much longer process of actually generating the hardware. This rapid verification saves an unbelievable amount of time compared to old school hardware design. So, let's zoom back out and really look at the big picture. What does all this actually mean for the future of technology? What it all boils down to is this. High-level synthesis is a democratizing technology. It's tearing down the walls that have separated software and hardware design for decades, giving a whole new generation of innovators an incredibly powerful tool to solve some really tough problems. And the impact is it's enormous. We're talking about giving a supercharge to algorithms for things like artificial intelligence, real-time video processing, complex scientific computing, you name it. It empowers software developers to start thinking like hardware architects, to think about the parallel nature of their problems, and to unlock performance they could never even dream of with the CPU alone. And that really leaves us with a fascinating question to think about. When the power to design custom-fit, high-performance hardware is no longer locked away with a small group of specialists, but is in the hands of millions of software developers all over the world, what incredible new technologies will they build? Something to chew on. Thanks for joining me.